Good morning, friends. We were developing perturbed equation of motion for lateral directional case, and the first equation you have already derived in explicit manner, and this is the second equation. Just to make you comfortable, I will again go through the second equation quickly, because these are all mechanical things, and once you have understood how to handle one, you know how to handle others. If I try to derive the second equation, we start with the equation Ixx p dot, this is the perturbed equation, minus Ixz r dot equal to LA, and what are these P and R? They are the perturbed rates, right? And LA is the rolling moment. Rolling moment means about the x-axis, body x-axis. Now, we are also clear that since we have written this equation, these equations in stability axis system, we know how to give a correction for Ixs and Ixz, so that appropriately we have taken the moment of inertia about the stability axis system. Now, we started with this, and we know that LA I can write as half rho v square, or let us say u1 square SB into CL, and CL is function of P R beta delta A delta R, and then we wrote it like half rho u1 square S into CL P into PB by 2 u1 plus CLR into RB by 2 u1. You are expert now why you are multiplying by B by 2 u1 to non-dimensionalized P and R, which are the rates. So if I can put R like this, then CL beta into beta plus CL delta A into delta A plus CL delta R into delta R. Right? Let me write the notation consistent. Okay. Now, if I write this P dot equal to, this will be equal to what? So, I have to multiply left hand side and right hand side by Ixs. So, I remove this Ixs from here, and then there will be Ixs here, and then there will be Ixs here, okay, which in turn means there will be Ixs over the right hand side, and now I can write P dot minus Ixs by Ixz by Ixs. This we are writing as, denoting as A1. So, minus A1 R dot equal to half rho u1 square S B into divided by 2 u1 into CLP by Ixs. This we are writing as LP. So, what is LP? From here you can easily see LP is nothing but half rho u1 square S B. Here B will come, B is missing, okay. This B is here, so this B should be here, half rho u1 square S B into CLP, right, into B by 2 u1 Ixs. So, this B into B become B square. That is the way you can write in a simplified version. So, L beta or LR, let us say, I maintain the order, LR into R plus L beta into beta plus L delta A into delta A plus L delta R into delta R. As simple as that. So, that is what exactly is your second equation. Similarly, you can find the third equation. Please, as in flight dynamics man, equations are fine. You need to know what is n beta, who decides n beta. You know, in n beta there is a Cn beta. What is Cn beta? Cn beta talks about directional stability. Cn beta has to be greater than 0. You also know if I make Cn beta very large positive, then it will become very sensitive to wind, because Cn beta is greater than 0. Directional stability, if there is a wind like this, it will try to neutralize beta, it will turn like this. So, very, very sensitive. This frequency, your frequency will go on increasing, right. Like for a longitudinal case, if Cm alpha is more and more, its longitudinal natural frequency goes on increasing. So these are the understanding you should have. NP means damping, roll damping. That is, the moment you try to bank like this, a damping which will try to discourage this roll, or it will come fast, or come faster to the equilibrium once the disturbance is withdrawn. Once I know this, and you know that, if I am happy with this equation, I want to work in frequency domain, I apply Laplace transform, and then once I apply Laplace transform, then the equation will take of the form which is as it was done for longitudinal case. The equation will look like, let me write that, SU1 minus Y beta minus L beta minus N beta. Here it will be minus SYP plus G cos theta 1 S square minus LPS minus S square B1 plus NPS, and here it will be S, let me write this, YR minus S square A1 plus SLR S square minus SNR, this into beta of S by delta of S, this is phi of S by delta of S, and psi of S by delta of S. This is equal to Y delta, then L delta rolling moment, and N delta. I have put delta here because you could see here there are two control surfaces, delta A and delta R. So if we are taking only delta A, then this delta becomes delta A. If only delta R, delta is delta R, and you can take both of them together. How this equation have come? I took Laplace transform on this. So first equation will become what? S V of S plus U1 R of S is equal to G cos theta 1 into phi of S plus Y beta into beta of S, similarly YP into P of S plus Y R into R of S, then Y delta into delta of S, and Y delta R into delta R of S. Similarly, I can do it here, I can do it here, and then if I combine them, I can write this in this equation form, matrix form. And you know now that if I try to find the characteristic equation for this lateral directional case, that corresponds to the determinant of this equal to 0, right? And you find the roots and then comment. That is the principle we followed, procedure we followed, longitudinal case also. Before we go to that, just one more attention I want. Whole of this matrix, here it is beta, phi of S and theta of S. If we want to write it in terms of beta, phi and psi dot, in this form if we want to write, and you know for our case, this is the steady state and disturbances like this about steady state. For us, psi dot is equal to R. Your rate and psi dot are same. But if there is a bank and then there is a psi dot, they are not same. But it is like this. So psi dot and R are same. So what you can do, if you want to write the same equation using psi dot, what will be the change? You could see is for R, we have used psi dot. Now psi dot is a motion variable, then only changes that you will get is wherever this is coming here, if this is psi dot, then this term 1s will be less. So this term will be minus S A1 plus LR, and here again 1s will be less, that will be S minus NR. Clear? Here it was psi dot, which is equal to R. Now, if I am putting psi dot as a variable, then that one S will be less from the expression which are getting multiplied with psi. So, this is one is here. If you see this, this into this into this first, with this one, this into this and this into this. If it becomes psi dot, then this S also will go. So, it will become U1 minus YR. Similarly, here one S will go. So, this will be this, and here one S will go. It will be like this. So, the whole matrix, if I am writing using psi dot, then one S will be less in this column. Okay? Now, that is this concept we will use later. So, I thought now I will explain you. And now, if I see, if I try to write the determinant of this matrix equal to 0 to have the characteristic equation, then what I get is as simple as the determinant I get as S into again A is 4 plus B S cube plus C S square plus D S plus E equal to 0. Although now the expression for A, B, C, D, E will have the stability derivative, inertia derivative or dimensional stability derivatives which belong to this stability matrix, right. And you know that we will be giving you that expression. Just for completion, one expression I will give you. This is lateral directional case. So, here A is given as U1, 1 minus A1 B1. Similarly, the important is E is G cos theta 1 into L beta NR minus N beta LR when there is no thrust. Okay. All this detailed expression I will be posting, so that you do not try to remember this, try to understand this. In one page, I will be putting all those expression for longitudinal, lateral, etc., right. Let us understand what is more important for us. If this is agreed, understood, then now we could see that if we want to find out the roots of this equation determinant equal to 0, then what do I get? Let me erase this. I get S equal to 0 and A is 4 plus B s cube plus C s square plus D s plus E equal to 0. S equal to 0 is the case, it is a lateral directional, it is like a neutral stability when it referred to psi. See what the airplane goes like this, goes like this, goes like this, aerodynamically they are neutrally stable, like no change, right? Okay, no resistance, because for airplane it is a relative airspeed. So, psi 2 degrees flying, psi 3 degree flying, psi 4 degree flying is the same thing. So, we call x equal to 0 suggests that, so we neglect that, okay, we understand. Now, from this again, if we have to apply Routh criteria, and you know Routh criteria A, B, C, D, E greater than 0, this to be satisfied. For Routh criteria A, B, C, D, E should be greater than 0 and D into BC minus AD minus B square E greater than 0. You also understand, for example, if E is less than 0, that means one root has come, real part has come in the positive side. Okay. So, all those details we know. Now, what next? In longitudinal case also, we have seen, we have given some attention to the expression for E. Okay. Before we come to that, we know this solution for this equation AS4 plus BS cube plus CS square plus DS plus E for lateral directional case. This is lateral directional case we are talking about. Generally, we expect one, all roots real, or it could be 2 real and 2 complex conjugate. Third possibility is all roots complex, that is 2 pair of complex conjugates. Please see here 2 complex conjugates, but here 2 pair of complex conjugates, right? With already in second case 2 real roots are there, right? Mostly what happens, this case 2 is the common type of root we get for most of the airplane, and that belongs to, mostly you find for lateral directional case we get this case 2 real and 2 complex conjugates, right? And if you see that, if I give a closer look to E, where E is G cos theta 1 into L beta NR minus N beta LR, this has to be greater than 0 for satisfying dynamic stability criteria. What is seen that if it is not greater than 0, then there in time domain there is one divergent root. On divergent, what we found that if E is not greater than 0, so say E is less than 0, then we find there is a divergence in the solution, which suggests dynamic instability, and that is typically the spiral divergence. And typically what happens in a spiral divergence, if this is the airplane, right, because of bank disturbance, the airplane starts side slipping. As it side slip, beta is introduced, it turns like this. As it turns, there is another lift, so it again left wing becomes more having cut. The spiral divergence, try to understand, the airplane is moving like this and there is a bank disturbance. As there is a bank, it starts side slipping. As it side slips, there is a beta. The moment there is a beta, the airplane tries to turn like this. And as it tries to turn like this, the left wing gets more velocity, relative air velocity. It further banks and again further turn like this. So it goes like this. Until you ensure that E is greater than 0. If E is greater than 0, then you avoid spiral divergence. Most of the airplane is having a very weak root in spiral divergence, so it is manageable by the pilot. Don't worry about too much about it. But fundamentally what we understand, the combination of L beta NR minus N beta LR, this should be greater than 0. So CL beta plays an important role, CNR plays an important role, Cn beta plays an important role, and CLR. So you could see these 4 derivatives are to be created in the airplane through layout of your tail, wing, and etc., such that this is satisfied. Okay. So now you could see, although we are talking about CL beta for lateral stability in static sense, you could see that also plays important role in dynamic stability. So that is the connection. Okay. Now you come for exact solution. Again, this AS4 plus BSQ plus CS square plus DS plus E equal to 0. This is the characteristic equation, and for a typical airplane, business jet airplane, we found that lambda 1 was minus 0.00101, lambda 2 is minus 0.5 507 and lambda 34 complex conjugate, it is your case 2 plus minus 1.617 J. How did I get these values? We know this is the characteristic equation. We have an airplane whose aerodynamic coefficients are known, derivatives are known, inertias are known, or dimensional derivatives are known. And using the expression of A, B, C, D, E for lateral directional case, we got this equation, then solve numerically to get this. And you could see that typically most of the airplane, the roots are what we mentioned for the case 2, 2 real and 1 complex conjugate, or 2 complex roots. Both us, 1 complex conjugate is equivalent to saying 2 complex roots, so 4 roots. Now you could easily see here that these 2 are real, so there are no oscillations, right? However, this root, it is a complex conjugate, it has oscillation. And also you could see the real part is not as negative as short period real part. Okay? So once I understand that now what type of response or dynamic response I'll be expecting, I need to understand what is first one, the weak root, and that is spiral divergence or spiral root, sorry, right. Second one is roll, which belongs to the roll damping, roll dynamics. That is, if I give an aileron input and withdraw it, it will come back, right? Okay. No oscillation, please understand. Now we try to get more insight about lambda 1, lambda 2 and lambda 3, 4. You could see lambda 1, I can clearly write it is a slowly convergent first order called spiral mode. That is the lambda 1, weak. Right. Lambda 2 will say a highly convergent. Why convergent? Because negative. See, this was also convergent. The value was so less, so it is slowly convergent. Here the value is large, so this is convergent because of minus, but magnitude is large, so you say highly convergent. First order, of course, first order you could see here, and this is called roll mode. Okay, or rolling mode. Right way I should use rolling mode or roll mode, whatever you like to. And the third one, third and fourth, this pair, it is slowly damped. Again, you see slowly damped. Why slowly damped? First of all, why damped? Because negative. Real part is negative. Slowly because magnitude is very less. Slowly damped. Then moderately low frequency oscillation called Dutch roll mode. Dutch roll mode. Let me write clearly here. This lambda 3, 4, what are the keywords? One is slowly damped. Number 2, second word is moderately low frequency, that you could see from this value of this. In combination, you know how to find out the frequency. You have to again treat it as a second order system, the s squared plus 2 zeta omega n s plus omega n s squared equal to 0. You will find these are moderate low frequency, and this is also called Dutch roll. This is called Dutch roll mode. Okay. Typically, approximately, see, this will go on doing like this. This oscillation, and then like this combination, this one, this goes here. So, this sort of a combination, little bit of bank, right. Actually, it is combination of everything. In approximation, you may neglect one of those, but primarily this is this, and one is going like this, their combination. Okay. So, you get some sort of a oscillation like this. Okay. That is a Dutch roll. So, what we learned now, we said that for lateral directional case, for most of the airplane, the roots are of this nature, one weak first order and the strong first order, and this is a complex. This belongs to roll mode, this is spiral mode, and this is the Dutch roll mode. Right? We will go one by one to understand what exactly it means. Now, let us play around with this lambda 1, lambda 2, and lambda 3, 4. So, if I write lambda 1 is equal to minus 0.00101, and lambda 2 is equal to minus 0.507, and lambda 3, 4 as minus 0.0580 plus minus j 1.617. Then I know these two are first order, this is second order, so I can write the equation in the form T1s plus 1, T2s plus 1 into s square plus 2 zeta 3 4 omega n 3 4 s plus omega n 3 4 square, this equal to 0. This is the characteristic equation, this is second order, this is the two first order, right. And if I do that, then from this I get the root lambda 1 equal to minus 1 by T1, lambda 2 equal to minus 1 by T2, and lambda 3 4 I can write like this, zeta 3 4 omega n 3 4 plus zeta omega n 3 4 1 minus zeta 3 4 square. Either you do it like this, or for second case you understand I find the two roots and form equation x square minus sum of the roots into product of root equal to 0. So, that way also you can find out. Choice is yours, right. If I do that, then I get the solution as T1 equal to 991.8 seconds, T2 as 1.972 seconds, and omega n 3 4 I get as 1.62 radian per second, and zeta 3 4 I get as 0.036. I hope you understand. I can write this equation using these roots in the standard form, and first root will be T1 s plus 1 equal to 0. So, from there one root, from another root, and from there I can get one complex conjugate, and then you know how to handle this to find out omega n as well as time constants, right. Okay. So, that confirms to our point that this is slowly convergent, takes so much of large time. This is fast convergent, and this is having a natural frequency and damping ratio is low. So, it is not highly damped, slowly damped, okay, which is a Dutch roll mode, right. With this, we have just concluded through an example how to handle lateral directional dynamic case by solving exact characteristic equation which is given by what is written AS4 plus BS cube plus CS square plus DS plus E equal to 0. We also identified that generally most of the airplane will have roots of this nature, 2 real and 1 complex conjugate, and we know how to identify which one is spiral mode, which one is roll mode or rolling mode, which one is Dutch roll mode, right. So, next we will go for approximation. Thank you very much.